If you consider a line being of finite size like laser pointer, the line beam will propagate like this. So most of the light wave from the pointer, they propagate very close to the z-axis, right? So under this situation, we will use partial approximation. The partial means that the wave propagates very close to the propagation axis. Okay, so consider if we assume that the z is our propagating axis, then partial approximation means that the wave propagates very close to the z-axis. If we define the k vector of a wave is like this, and the k vector has a theta angle with respect to the z-axis. Partial approximation deal with wave that if the angle theta is very small, so for this situation, we can treat the wave under the partial approximation. And such kind of wave, we call it is partial propagation. For such kind of partial propagation, you can assume that due to the k vector is very close to the z-axis, the z component of k will be very large compared to the kx and the ky. So we can say kz will almost equal to the k. And then k sub s and k sub y, these two components will relatively very small, and they are very smaller than the k. So this is the so-called partial approximation. If the wave propagates very close to the z-axis, then the kz is almost the same as k, and the ksky will be very small. For this kind of situation, let's go back to what we have said in previous slide. We said that the square of the three components, the summation of these three will be equal to the k square. So here should be z. And by this property, we can say that the kz can be expressed as k square minus kx square minus ky square. And then we take the square root. We take the k square out from here, then we will have this expression. And for partial propagation, as I have said, kx and ky will be very small compared to k. So this term will be very small compared to 1. And we have learned that if you have 1 plus n to the order of 1 plus x to the order of n, if s is very small compared to 1, then this term can be approximated as 1 plus n times x. Okay, so if s is very small compared to 1. This can be approximated as this one. So following the same rule, I have told you this term is relatively very small compared to 1. So we can approximate this term as k times 1 minus, take this term here and times this term. Okay, so let's rearrange it. For partial approximation, the kz component will be approximated as k minus kx squared plus ky squared divided by 2k. This is the approximation for the partial propagation. So if you deal with plane wave under for partial propagation, then you can use this partial approximation to replace kz in this way. So for plane wave under partial propagation, we can define the phi of xyz in this form. Because in partial approximation, the field will almost like propagate along the z-axis. So if you define the phi function in this way, we will know that the exponential part here will be a fast varying term. It will change very fast as propagation. And the amplitude function here then will be a slowly varying term. It will change slowly. Okay? And then let's go back to the phi function. The phi function can be expressed as a superposition of plane wave. So we can write it in this way. Okay, as you can see, we have expressed the phi function in terms of a lot of plane waves. So this expression just based on that any function can be expressed as the linear combination of plane waves. So by changing the kx and the ky, we can obtain all kinds of plane waves, and then the phi function is expressed as the summation of all kinds of plane wave. Okay, the integral here means the summation. You may wonder that you have used the kx and the ky as a parameters to form the integral. Why we don't have kz here? Why we don't have dkz here? As I have said, the kx and the ky and the kz, these three components are the three components of k. They have the relationship that kx squared plus ky squared plus kz squared is k squared. So if we fix the value of k, then as you change kx and ky, then you will obtain the corresponding kz. What I mean is that for fixed k and a set of k's and ky, kz will also be fixed. Okay? So the integral here just has dks and dky. Then we take this expression back into here. The phi function can be written in this way. So we write it as u of x, y, z times exponential minus jkz will be equal to, here we will take the partial approximation into this integral. Okay, so we will express the above integral by using the partial approximation. As I have mentioned, the partial approximation is you can replace the kz in this form. So let's do it. As we want to replace kz in this form, for ks you can write it as exponential minus k sub s times s. For ky, it will be exponential minus j ky times y. And here, you can take the partial approximation into kz. It will become exponential minus j kz times exponential positive j times 2k k square plus ky square over 2k times z. Okay, and dkx and dky. These two terms represent the exponential minus jkz here, and the kz for the partial approximation, it will be k minus 2 kx square plus ky square divided by 2k. So this is why we write it in this way. Okay, then compare the result on the left hand side and the right hand side. You will see they have a common term, as I use the red curve. So these two are the common term. Then we can say that the u of x, y, z is then can be expressed as the integral of capital U sub 0 kx ky times exponential minus j k sub s times s times exponential minus j k sub y and times exponential this term. Okay, so if you can find out the result of the integral, then this means that you can find out the result for the u. And as you can find the result of u, you will obtain the E field and the H field. So in chapter 5, our purpose is to find out the result of the u function to obtain the E field and the H field. How to find out the u function? You just try to perform the integral like this. Okay, but this integral is too complicated for us. We must to simplify it. Before we simplify it, we have to know what will be the meaning of the capital U function shown here. So I will discuss the meaning of the capital U function later.